how many of you guys have looked inside of your computers? You see this kind of black cartridge. It looks like a, let's see, is it Nintendo? Yes. I guess the Nintendo game cartridges kind of look like the Intel Pentium cartridges that they put into the slots. Well, if you were to take apart one of the cartridges for the Pentium 2, I'm not sure what the case is for the Pentium 3 and the Pentium 4, what you would see on the inside is a chip, which is the actual CPU, and then you would see two other chips that are fairly big on the outside that are still part of that circuit board that's on the inside of that black cartridge. Now, of course, don't do this at home unless you plan never to use the cartridge again. But if you happen to have one lying around, I recommend that you open it up and take a look. And what's inside of that thing is, here's the processor and the registers and the level 1 cache all on the same die. Okay? And then off that chip, but before it goes to the really big wires that are on the motherboard of the computer, is the level 2 cache. And that's sitting right here on the same little card that the processor chip is mounted on. And so the idea is that the wires in between here and here are fairly short. And furthermore, since Intel makes the whole thing, they can control very well the manufacturing of the circuit board and make the characteristics of those wires very well known. And so they can try to get the latency, the transmission time between this level 2 cache and the level 1 cache as short as possible. Yeah?
How big is that? Just so I can get a scale.
Let's see, around this large, roughly.
Okay.
So, kind of looks like this. We could open up this box here and kind of take a look. But it's, if you think about a,
yeah, but you can see how big it is.
Yeah, it's sort of like the same size as a Nintendo 64 game cartridge. You know those little gray cartridges your kids put in? It's roughly that size, a little bit less. Yeah.
If L1 cache has 1 nanosecond latency and memory is 60, what is L2 cache?
L2 cache, I don't actually know, but I would guess it's on the order of 10. Something like that, okay? Again, it changes all the time, and it changes depending on how fast the processor is that you're going to put in there. So, okay, and then you know that once you go off of this board and onto the main backplane of, or not backplane, the main motherboard of the computer, there are slots for DRAM that look like this. And the wires between here and there are longer. And what we're going to talk about today, and we talked about all this stuff last time, what we're going to talk about today is how this DRAM can in fact be a cache for the disk. And how in fact the 32-bit memory space is going to exist not in the DRAM. We're not actually going to have 4 gigabytes worth of RAM in most cases. We're going to have less than that. But we are going to reserve potentially up to 4 gigabytes worth of disk space for the virtual memory of our machine. Now, the question is why 32 bits, okay? And this is almost becoming a moot point now because the newest processors that are about to come out are not 32 bits in width, but 64 bits in width. And 2 to the 64 is a big number. And so the question is, you know, none of us are running programs right now that are 4 gigabytes in size anyway, okay? We do have disk drives that are that big, and some of them are much bigger than that, or like 80 gigabytes, for instance, is sort of the most recent big disk that you can buy with your system. But the question is, why should the computer have an address space that's so big? And historically, computers have always been made with kind of optimists amongst the engineers, okay? For instance, you know, when I'm trying to remember whether it was the EDSAC or one after that, in any case, it had, some machine there had around 512 words of memory. And they said there's no way you could ever need more than that, okay? Because after all, there are no programs you could possibly write that would need more than 512 words. Well, of course, that sounds totally ridiculous now. But 32 is 4 billion words of memory. Why do we need so much? We don't run programs that are that big. We don't use data that's that big in general. So why do we need so much? And the answer is, well, of course, we know that Microsoft next year is going to double the amount of bloat that they have in their software. And if we do that every year, another doubling and doubling and doubling, pretty soon we're going to be up. But that's sort of a joke, right? Why 32 bits? And when you think about it, first of all, answer number one is you can never tell. Okay? And the history of computer architecture is full of examples of people saying there's no way they could use more than 16 bits. There's no way they could use more than 18 bits. There's no way they could use more than 20 bits. Who knows the story of 20 bits on the IBM PC? Anybody know that? Yeah. What is the story of 20 bits on the IBM PC?
Yeah, as I remember, for backwards compatibility, they require the programmers to always keep track of 20 bits. They would turn that into a 24-bit address, if I'm remembering.
Well, there's this really terrible thing. When the IBM 8088 first came out, the Intel 8088 first came out, which was the chip that was used in the first original IBM PC. Okay? It's also the same as the 81, it was just the 8088. Okay? This was before the 186 and the 286 and the 386 and so forth. The guys at Intel said, well, we're just designing a little rinky-dink microprocessor here. This isn't a mainframe. And there's no way that the user is going to use more than 20 bits of address space. Okay? 20 bits, as you know, is 1 megabyte, right? 1 meg is 2 to the 20. And so that's how large the DRAM in your system could get. And actually, if you run a IBM PC in the standard mode, the most that you can address is 20 bits. And then when the 286 came out, they had to have all these crazy kind of ways for you to have a 1 megabyte window into a memory system that was much bigger than that. And so it became hard to break this 1 megabyte barrier. It moved up to 24 bits, and each time they kind of bumped it up a little bit more and a little bit more and a little bit more. And finally, with the 386, they came out with what was called protected mode. And this was a new mode for the processor to operate in which case it had access to all of the memory and didn't have to look at it in terms of a 1 megabyte window at any given time. Anyway, it's just this terrible, it's just a shameful thing if you think about it throughout the history of processor design, where people seem to think, well, there's no way that they could use more than X. Okay? So the trend nowadays is to say, let's always overestimate how much space the person could use. How many people have run into problems when installing a hard disk in a system where the BIOS of the system can't handle the fact that the disk is bigger than the BIOS thought it could ever be? Anybody have that happen? Right? So what is it that you need to do? You either need to, now the BIOS in a computer, just to let you know what that is, it's a program in the read-only memory of a computer, and it basically tells the computer what to do when it first starts up, and also has handling routines in there for how to do reads and writes to the disk drive, and reads and writes to the keyboard and the video system and things like that. Well, typically what has happened is that when the people write the BIOS for these things, they say there's no way that a disk will ever get bigger than 1 gigabyte. This is back in 1982, let's say. And of course, the day comes and the disks do get bigger than 1 gigabyte, and all of a sudden the BIOS can't talk to that disk anymore, and you can't boot off of it anymore. And it's a big hassle, and the people that sell bigger disk drives sell special pieces of software to kind of fool the BIOS into thinking that the disk is smaller than it actually is. Okay? And then the other option is you can go and you can try to get a new chip for your computer with a new BIOS, or these days you can actually download new software to update the BIOS of your chip. But anyway, that's reason number one. Reason number two for why we want the address space to be big is because large address spaces are convenient. Okay? Now let's think about this in terms of addresses for people's houses. Let's say that I was designing a city, and it started out sort of as a kind of a, I don't know, farm town, right? And the houses were spaced fairly far from each other. How should I number the addresses of the houses? Should I number them 1, 2, 3, 4 as I walk down the street going through big fields from one house to the next? Or might I want to number them 100, 200, 300, 400 because I had some idea in my head that someday sprawl will come to the wonderful farm town and fill in those spaces in between the houses, And this way I could put more stuff there. Well, it turns out ideas that are similar to that happen in addressing things inside of a computer as well. It makes sense often to have the address space of a computer filled very sparsely, okay? Because it allows for new data items to go in between the items that are there now, okay? Examples of how this is set up. Sometimes, for instance, I would like to have a program, and for instance, I may want to have access to a file, and that file may be extremely big. I don't know what part of the file that I want, but the easiest way for me to have access to the file is to say, just take the entire contents of that file and map that file into the address space of the program. And then the program can access the contents of the file just by doing loads and stores, and not by doing special operations to read and write the disk. And that's a tremendously powerful way to access files, and it's called the memory mapped file. In order to do that, my address space of the machine has to be big enough that a file, no matter how large, can fit in it. And again, we're seeing that 32 bits may not be big enough, because this says that the biggest file that I could map in, assuming the program was very small, is what? 32 bits worth of stuff, or 4 gig, right? And some files might be bigger than that. So here's a reason why I might want to go to 64 bits. Another incredible idea is with inter-process communication. How about mapping into the address space of one program all of the possible variables that are going on in every processor throughout the entire world? What's so bad with that? And that way, if I want to talk to a processor in Pakistan, okay, I go to address space such and such and such and such and do a load or do a store. And those reads and the writes to the memory system would, in fact, cause communication over the internet, which would then cause data to come back and forth there. And that way, my one piece of software could treat everything out there in the entire web as available to me simply through the means of reading and writing memory. Kind of a wild notion. What if I wanted to map every web page that's ever been written into my memory space? Wild, wild notion, right? Every file that's ever been written in the whole world. Can I fit that in 64 bits? 2 to the 64. How big is that? That's, well, 2 to the 32 is 4 times 10 to the 9. So 2 to the 64 is 16 times 10 to the 18th. Okay, how big is 10 to the 18th? That's a pretty big number. Do you think that the number of web pages is less than this? Do you think the number of characters that have ever been typed in the world is less than this? No. That a human being has ever typed? No? How many people are in the world? 4 times, what is it, 6? Sorry. Well, you know, times change, right? 6 times, people have been busy. 6 times 10 to the, what? 9 people per Earth, okay? Okay. Okay, that's a pretty small number. How fast can you type? 1 character per what, second?
60. No, if you're an accomplished typist, you can do 100 words a minute.
Yeah, but on average, you know, you have to sleep some of the time. You gotta 10 characters a second?
No,
That's
10 words a minute.
10 words a minute.
So
But
1 character a second.
let's say 1 character per second. How many seconds in a year?
31.
Pi times, ooh, somebody remembers. Oh boy, this is great.
Just do it on that phone.
Pi times 10 to the 7 seconds per year. And we're going to do 1 second per character, okay? Okay. So what do we have here? 10 to the 7 times 10 to the 9th is what? Well, we're going to assume that everybody is typing in the entire world. Everybody's just going pick, 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 right? Okay, 10 to the 7, 10 to the 9 is what? 10 to the 16th. 6 times pi is 18. Okay, so if everybody typed for an entire year, 1 character per second, and this is every man, woman, and child down to the smallest baby, right? Typing constantly for a year, okay? 5 times 10 to the 16th. We still have more address space than everybody typing for a year. In fact, we're over by a factor of 100. So we could go for 100 years of people typing throughout the entire world, and we could store everything.
The typewriters have been around since.
Uh-oh, typewriters haven't been around for 100 years.
They have.
Oh, the typewriters have, but not these kinds of typewriters. Okay, wild notion. A 64-bit machine could map in everything that's ever been written.
But not,
By humans.
but it looks
By
like,
humans. Oh, sorry,
There's
no.
also computer generation of reads of data.
Okay. Okay, true. And of course, when someone makes a copy, that's true too. But this is an incredibly big number, okay, and I'm assuming a whole lot here. And I'm willing to bet that if you took everything that's ever been written by either man or machine, it's still less than this. Okay. An interesting question is how much disk space is in the whole world? Okay. So there's 6 times 10 to the 9 people, right? How large of a disk could each of them have if we were going to have an address space that's this big? So we're going to give every man, woman, and child on Earth a disk drive. And we want to make up an address space that's this big. We want to store that many bits. How much of a disk drive do we have to give to each person? Well, 6 and 16, let's say it's a factor of 2, right? So it's 2 times 10 to the 9th bytes, right? Which is 2 gigabytes. Okay. So if we went and gave a 2 gig drive to every person on Earth, we would actually have a 64-bit worth of space worth of storage. What's that? And it would all be full within a few weeks. Yes, but what would be on most of those drives would be copies of Microsoft Word, right? And they'd all be the same. So it doesn't count. The information content would be extremely small, okay? If they're just if they're copies of each other. How much of your disk space do you think has stuff that you've added, roughly, for any one of you?
Stuff that we've actually created.
Stuff that you've created, not copies of Microsoft Word. Several gigs? Oh, come on. You've been typing fast. My guess is that it's less than 100 megabytes, even for the best of us, okay?
graphics and music is,
Yeah, but in order to, yeah, okay, it's true. But still, this is every man, woman, and child on earth. Well, this discussion is fun, okay? Someday we'll go to 128-bit machines, and then I challenge you to do anything, okay? Because then we're down to counting how many particles there are in the universe, okay? So that's a pretty big number, too, but not as big as that.
How big a number is that?
The number of particles in the universe. Do you know, Sam?
Under Google.
Under a Google, and a Google is 10 to the 100. So less than 10 to the 100 elementary particles. Well, you know, that's only a few factors less, so that's only going to change us by a few particles in the universe, per universe. Okay, so when we get to 2 to the 128, we're really getting up there, right, in terms of the amount of storage. And we could have an address space that was 128 bits wide easily, simply by making our bus only 4 times bigger than it is now. Okay, and we may want to do that. And the question is why? Well, the answer is that it means that we can create a structure that is extremely sparse but very easy to access. It would be fantastic. I think it would be an amazing thing to map the entire World Wide Web into one address space. Okay, because through loads and stores, I could access anything. And furthermore, here's another wild notion. If the address space was big enough, the addresses might not have to ever change. And what's wrong with the internet right now? What's the trouble with the internet? How hard is it to get an IP address? IP addresses are 32 bits, right? And what's the trouble with the IP address system? We're running out of space. Now, are we really running out of space? Are there more than 2 to the 32 machines? No. What's wrong is that they decided to segment the address space, right, and say the top byte means this, the next byte means that, the next byte means the subnet, and finally the byte that's left usually means the machine within the subnet. And so it was tremendously handy to sort of divide up this address space into big chunks, saying, you know, here's North America. Actually, what they really did was it. They said, this is North America, you know, and this is, you know, all of the rest of the world, right? You know, I'm going to put France down here because, you know, and Africa is going to be this tiny little piece down here at the bottom. And of course, they've run out of space because they've divided this up and certain parts have run out of space. Well, when the internet was created, do you know what the guy said? There's no way we could ever need more than 32 bits.
That's the same guy who...
It's the same guy who's given us all the other trouble, the 20 bits in the PC, all of these other things. So you get the idea that lots of bits is a good thing, okay? Okay. But, despite the fact that we're going to use a tremendously big address space, we can expect that that address space will not be very filled in. It's going to be sparse. It's going to be full of holes, just peppered with a few places that are used, but most of it is just going to be holes. And so when we design our memory system, we want to take that into account because, God forbid, we should be forced to buy 4 gigabytes worth of DRAM in order to make the machine work. Or if we have a 64-bit machine, we have to buy 2 to the 64 bytes or words of DRAM in order to make it work. So here's what we're going to do. We're going to pretend. Okay, so I have these little kids, right? They love to do this. And we're going to do the same thing. We're going to pretend, in the case of our 32-bit machine, that there are really 2 to the 32 bytes or words, depending on what kind of machine we have, of virtual memory. But we're only going to implement the memory that's actually used. So let's say this big stripe here represents the address space, and the white parts of the stripe are the places that are not used. And these little gray parts here are the places that are used. Okay? Our CPU will see this entire stripe, but we're going to fool it. We're going to have a little map that every time the CPU tries to access a given place in this thing, that map will translate a particular location in this large space into another location in a much more small place. And that map is going to be called the virtual to physical page table. And here's how it works. We're going to take the 32-bit address that's over here, and we're going to say, you know what? Let's divide memory up into a set of blocks that are going to be called pages, just like the pages of a book. And we will use the low-order bits of the address to specify where within a page we are. So as an example, if the number of low-order bits here was 10, we could specify anything between 0 and 2 to the 10 minus 1, which is a number between 0 and 1023. And that'll tell us where within a page we are. And this other bunch up here, these bits that are left, the higher order bits, are going to tell us what the virtual page number is, which of the pages within the virtual space we have. And those page numbers are going to be mapped to physical page numbers by a virtual to physical page map. So it takes a virtual page number in over here and converts it to a physical page number down over here. And notice that the number of bits over here is smaller than the number of bits up here because we're only going to implement in the physical address space those pages that are actually used. And in the virtual space, it's going to be a lot bigger. So the virtual to physical page map here converts particular page locations inside of the virtual space here to page locations in a memory that is much smaller than the memory here. Notice that where we want to access within the page is not translated. So if we want to go halfway down into the red page, that'll be halfway down into the red page here. Halfway down in the green page, halfway down in the green page here. Why are we doing this? Because of locality. Chances are that even if we're not using this part of the space, if we are using one part of the space of this red page, there's a pretty good chance that we're using other places near there. And so that's why this blocking into pages makes sense, because of spatial locality. Everybody get this? If there's any questions about the fundamental idea here, now's the time, because we're going to kind of go to the next stage. Okay.
Are you going to be explaining how that actual mapping occurs?
I absolutely will. In fact, it works like this. P is going to be the number of bits that we're going to use to determine the offset within a page. And the examples, since I can't write on this thing here, that I'm going to use here is that P is going to be 10. I'm going to do that just for now. Now, this is actually typical of technology. Maybe 5 years ago, the pages were around 1K in size. These days, pages have gotten a little bit bigger, perhaps 8K, perhaps even more. But for now, let's say that the virtual address comes out of the CPU saying, I want this thing, and this is 32 bits, okay? The 32 bits is going to come down here, and we're going to break it up into two parts. One's going to be the page offset, and that's going to be P bits, and that's going to equal 10 bits. And then there's going to be the virtual page number, and I call that V bits, or V bits. And since this is 32 and I'm stripping off the low order 10, how many do I have left? I have 22 bits left, okay? So how many virtual pages do I have? I have 2 to the 22 virtual pages in my system, which is how large? 2 to the 22 equals what? 4
million.
meg pages, virtual pages. And how large is each page? Page size equals 124, because it's 10 bits. 2 to the 10. Okay? Now I'm going to take the virtual page number, I'm going to put it into my virtual to physical page map, V to P, page map, and out will come, I think I used M, with the physical page number. That's M bits, which in this example, let's see, what should we use? Let's use 10. Okay? And then those will be combined to create the physical address. Which in this case is pretty small. That's 20 bits, or 1 meg. Okay, so I've gone from 4 gigabytes or words, depending on how this is set up. This is 4 gig up here, down to a physical size of 1 meg, which is great. And again, the assumption is that only 1 meg is being used out of the 4 gig, but the address space is big for the reasons we talked about before. Now this virtual to physical page map, all it is a table. Okay, it's a table, and I take my 22 bits of V here, and I go in here, and I'm going to read out the information that's going to tell me what physical page it is. So let's take a look at that. Here's what the table looks like. The virtual page number comes in here and tells us which virtual page we want. This is going to look a heck of a lot like a direct map cache, okay? Except we just take the virtual page number and find a particular entry in the table. We look it up and we find out what the physical page number is. We need M bits to represent that. We're also going to have 1 bit that's going to be the valid bit to tell us whether or not that page exists. And that valid bit better be off for almost all of the entries in the table here. Why? Because, as we said, the virtual space is very, very big. The number of rows in the table is very, very big. But the number of physical pages that are actually implemented is going to be smaller. Okay? And so for all of the virtual pages that actually are not implemented, for the ones that were blank in the picture before here, all the blank spaces here, that valid bit will be set to 0. Only for the pages that are actually mapped will the valid bit be set to 1.
This is hardware?
This is hardware.
How is it then that you can put an arbitrary amount of RAM in your computer?
Because it's, well, I'll tell you in just a second. Okay? We're going to talk about how large the table is and how, in fact, the table isn't what we think it is. Okay. So, what's the width of the table, it's m plus 1 bits. We need m bits for here and 1 more bit for the valid bit. And we expect only how many of the valid bits to be 1? 2 to the what? 2 to the m of the bits are going to be 1. How many rows are there? 2 to the v, right? 2 to the v is pretty big. So this table is going to be a pretty large thing. In the case where v is 22, it's going to be 4 million rows long. And a table like that is extremely big, and most of the entries in the table have the valid bit set to 0, and thus are not storing any useful information whatsoever. So what are we going to do to solve this thing?
So these physical pages are only RAM, they're not like hard disk kind of thing?
So far, they're only RAM. Okay, in a few seconds, I'm going to talk about how they're on the hard disk too. What we're going to do in order to make the table not as big is we're going to recognize that there are, in fact, big blocks of the table itself where that valid bit is 0. And that means that we don't have to bother to store those parts at all. We can just say this whole chunk has the valid bit set to 0. In other words, we will page the page table itself. We will block the page table up, which has 4 million rows in it, into pages. And we'll say which of the pages of the page table are valid and which ones are not. And for the ones that are not valid, we won't bother to store anything at all, other than the fact that there's nothing valid there. The idea, going back a few slides here, is that there are huge tracts of the virtual space that are wastelands, that have no data in them at all. In other words, many, many, many pages in a row, in fact, one whole page table page worth of entries in a row with nothing. And so we shouldn't bother to store those. And so a typical setup for that is for there to be 2 levels of page map like this here. And that makes the size of each of these maps much less. Okay, question?
When you say nothing, do you mean absolutely nothing or completely random combinations of ones and zeros?
Well, there's nothing valid there. The computer is not expecting there to be data there. It's never stored anything there. It doesn't expect if it does a load from there that it would mean anything.
But there's likely to be some kind of charge there.
Well, keep in mind we're talking about the virtual address space, not the physical one. So it's not that that storage even exists at all. The same way that an address for a house that hasn't been built yet, the house doesn't exist yet. So the bits don't exist yet for these places. We've just reserved the address space for them. What we're trying to do is figure out a way to map. You know, let's say that we decided, because Sprawl is going to go and build houses in between all of the houses that we have, that we're going to convert our houses to be an address of 1 million and 2 million and 3 million and 4 million. And let's say we wanted to build a table that went from your address to where you were on the planet Earth, okay? You might be tempted to say, okay, that's just a table. So if you're at address number 1, then you live here, and here's your GPS coordinates on Earth. You're at address 2, you're over here, right? And so on and so forth until finally you get to 1 million, 10 to the 6th, and finally there's a real house that's valid, and your GPS coordinates are here. Now look, you've just created almost 1 million entries, all of which, if they had a valid bit, would have the valid bit set to nothing. And then finally 1 set to 1, and then a whole bunch more set to nothing. And this is all to account for future growth. Okay? Should you store this part of the table? No. Let's go ahead and say I'll block the table up into pages, okay? And when there's a block that has 1 or more valid entries in it, I'll store that part of the table. But for all of the rest of these, I'll just store a little check mark saying that there's nothing there. Okay? So that's the idea of paging the page table itself. Another great example of this, the phone system, okay? Everybody used to live in area code 617 here, right? Wasn't that great? Right? You didn't have to remember, is it 781 or 508 or da-da-da-da-da, right? And I still can't keep track of these things, right? What happened, they said you couldn't possibly ever need more than 7 digits for eastern Massachusetts. It will never happen, right? We all live in 617. Then, of course, it did happen, right? So now they added more codes and more codes and more codes. And what's worst of all is that they caused us to change, right? Do you guys actually know the history of this thing? Right, so it used to be that all of Eastern Mass, right, was, so here's 617, and all this stuff over the left was 508. 413. Well,
617, 508.
But 508 is only 10 years old.
508, so then they added 508, right? And then recently they went and said, no, 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 what we're going to do is we're going to put 617 here, right? And then this is going to be 781, that's where I live. And then there's like a gazillion other ones here, right? Okay, I don't even know what they are, okay? But they made this so everybody needed to change, right? And then recently, do you know what they just did like a month ago? They said, guess what? This isn't good enough either. And so they're adding another half dozen area codes. But everybody got so pissed off from having to change so soon the last time that they're not going to force us to change, but instead they're going to distribute those throughout all of the different ones. And in other words, within my town, there'll be some phones that are 781 and some of them that are some other one. And they're going to force us all to dial all 10 digits for every single phone call. Okay, and some of you guys do that. And that's called the overlay system, which is actually better because it means that you don't need to ever change your phone number, the new ones. But they did the worst of all possible things here, which is that they forced us to change, and then they did the overlay, okay? So it's just the worst of all. But the reason this is so bad is that they didn't think ahead how many phones will people have in the future when they did this thing.
No, but isn't it also false and fair enough? You didn't want to dial like 10 digits. Like
Well, so there is this kind of a trade-off in between the two. Actually, what I really want to do is I want to pick up the phone and I say, let me talk to Shai, right? And it just figures it out, right? So, and hopefully in a few years we'll be able to do that. But, okay, paging the page table is a way of saving on the memory. Now, you asked whether or not this is in hardware. The answer is in some systems it is in hardware. In most systems, actually, the answer is no, it is not in hardware. It's in software. So this is a memory structure. These maps are in memory somewhere, okay? Except for a very, very small page map, which has to do with how the computer first starts up. So, for instance, the page map for the operating system itself may actually be stored in a known place that the hardware knows about. But the other page maps are typically in software-defined places.
Are each of these levels going to slow down our memory access?
You bet. And we're going to have to figure out a way to make that better. Okay? And we'll talk about that too. Okay. So that was idea number one. Now, idea number two is, besides having this map between virtual space and physical space, is sometimes that physical memory will not be big enough. And it's not just that we want the address space to be big, but sometimes the programs are going to be bigger than the physical memory of the system allows it to be. Now, the truth of the matter is that these days, when you buy a computer, it is hardly ever the case that you are running programs that are bigger than the physical memory of the system. Okay? And that's only due to the fact that memories have gotten really, really big. So when I buy a new machine at CompUSA and I get 128 meg of RAM, I could probably run everything, Windows and Word and Excel and Outlook and all that stuff, without having to go beyond that 128 megabytes worth of RAM. Okay? But the truth of the matter is that I can also run that system with 64 megabytes of RAM or 32 megabytes of RAM. And when I do that, how many of you guys know what happens? What tends to happen? The machine slows down. But why does it slow down? Do you notice the machine doing something that it ordinarily doesn't do? It starts using that hard disk, right? The hard disk starts flashing on and off and on and off. And what it's doing is it's using what's called the swap file, which is win386.swp if you run Windows. And it is only storing a fraction of the memory of the computer that's active in the physical memory of the machine. And the rest of it it's putting out on the disk, swapping it out to the disk. And so there's really two ideas here in this virtual memory system. One is that there will be a translation between the address space, which is big, and the physical space, which is small. And then the second idea is that that physical space will be broken up into two halves, the stuff in the DRAM and the stuff on the disk. And in general, if there's not enough space in the DRAM for everything that we want, we're going to put some of it out to the disk. And just as in caching, we're going to be putting out to the disk the stuff that we're not likely to need very often. Okay. And so again, the same idea in terms of locality. We will define what's called a working set, being those locations in the physical memory or in the memory of the system that we will tend to want to have around at any given time. Okay. So here's what we're going to do to our page table to allow us to do that. In addition to the valid bit saying whether or not this page exists at all, we will add another bit saying, is this page resident? Okay. Is it resident in the physical memory of the computer, in the DRAM? Or if that resident bit is 0 and yet the page is valid, we will say that the page is on the disk and not in the RAM. And so pages of memory that do exist, that are occasionally used, but not very often, will end up being swapped out to the disk. And in that case, the physical page number will refer to where on the disk they are, not where in the physical memory they are. Kind of a simple notion.
So when we're reading from disk, are we still reading the full page
Yes.
back in each time?
Yes. Yep. So again, this is very similar to the idea of caching, except that the block size is 1 page. Okay. So whenever we have a fault, in this case it's a page fault, not a cache miss, we're going to say, okay, swap out one of the pages that are in there and swap in a new page and get the entire page in, even though you only wanted one word out of the whole page. And again, that's because disks, even more so than DRAM, have tremendous disparity between their latency, how long it takes to wait for the bits to come around and the head to move, and the rate at which the bits come in once you get there. So if you're going to get one word off of a disk, you may as well get the whole page, because you can get that in just about the same time. So that's how the resident bit works. Is it resident in DRAM, or is it sitting out on the disk? Furthermore, we will occasionally want to be somewhat careful about allowing our program to write certain locations either in memory or on the disk. As an example, we may have in the virtual memory of a program two sorts of things. We may have parts of the operating system mapped in to the address space of a particular program that is running. Now, Windows has been bad about this in the past. Windows 2000 is better than it used to be. The Apple Mac is awful with regard to this, but Linux is in fact very, very good. In Linux, a user program that you're running cannot arbitrarily write locations in the program that is the operating system that's running the rest of the system. And in general, a program in Linux can try to wreak havoc as much as it wants, and with few exceptions, it can't affect anything badly. The worst that it can do is kind of slow things down, okay, by making lots and lots of copies of itself and eating up lots of space, but it can't actually damage the other software that is running. And so we may want to have in the page table itself an additional mechanism for the protection of one program from another that is running simultaneously inside of the system. And we do that by adding another column to our page table here, which is the write enable column. And if we set that bit to a 1, then the program is allowed to write that page. And if we set it to a 0, it can read the page. For instance, it could run code out of the page, but it is not allowed to write it. Another example of where this would be used is, let's say that we had multiple copies of the program Word running. And you guys know you can run multiple versions of Word and have several windows up. There's no reason that we have to have separate copies of words in the memory of the system. We could just have one copy and many different PCs running through that one copy. Each copy would have its own page table like this, and the part of the memory that was devoted to the instructions of the program Word would have the write enable bits turned off. And as a result, the programs could not interfere with each other by writing to each other's copy of Word, which is a good thing. So it's kind of neat. You can use this page table for all kinds of stuff. Okay, let's talk about the performance of the paging system. And this is really an amazing thing. We talked about how the hit rate in a cache last time was in the high 90s. Not very high, but typically high 90s in terms of percent hit rate. Here you remember the cost, but what's important for this slide here is the latency. Now, DRAM is 60 times slower than the static RAM that we're going to use for the cache. That's pretty bad. How much slower is the disk than the DRAM in terms of latency? Well, it's on the order of 200 times slower, perhaps 1,000 times slower, depending on the magnitudes here. Okay? That is a lot slower. In fact, I'm even wrong than that. That's wrong. Nanoseconds to microseconds is 1,000. Microseconds to seconds is 1,000,000. So microseconds to milliseconds is another 1,000. So it's on the order of 1,000,000 times slower. That makes more sense. 1,000,000 times more slow. Maybe only 200,000 times slower. If you say this is 60 and this is 100. But that's a lot. That means that when we get a miss in the main memory of the system and we need to go to the disk, this T sub s is so big that even if alpha is almost 1, when we multiply 1 minus alpha times T sub s, it's going to drag the access time up incredibly badly. And that's why it is that when you only have 32 megabytes in your machine and you're running Word and Excel and all these things, and you see that disk light flashing all the time, why the system just slows down incredibly. It just goes, oh, God, it's slow. And that's why adding more DRAM to your machine gets the hit rate up for paging, okay, for the virtual memory system, in such a way that you have drastic improvements in the performance of your system. If you can arrange to never have to go down a disk, in other words, for alpha to be 1, and 1 minus alpha to be 0, then your average access time will just be T sub f, which is pretty fast.
I don't know if it's the same on a PC, but on a Mac, when you run a program, you can set how much memory that program wants.
Yeah, that is so bad, you have no idea.
What's going on with that?
I don't even want to talk about that. Okay? That's how bad that is. Okay? That is the most rinky-dink stupid thing I've ever heard of. Okay? Every modern operating system figures out as a program runs how big it should be. Okay? And the program is allowed to grow and ask the operating system for more space. Only on the Apple, which, again, remember that both the PC and the Mac were designed originally from sort of toy systems, okay, which were sold to people like, like me, that were willing to fiddle around with the numbers like that. How much memory should this system, program take? It just sort of reserves that much space in the virtual memory system, okay? But modern systems never do that. They start out small and they allow it to grow. Here's a little graph here, T sub s and T sub f, and as alpha goes between 0 and 1, the weighted average of the average access time will go between T sub s and T sub f. If alpha is 1, you'll get T sub f. If alpha is 0, you'll get T sub f. If alpha is a half, you'll get a weighted average of a half of the two of them. Okay, so that's just a graph of that. Let's figure out what alpha needs to be. If we assume that what we want is for our system K to perform with twice the average access time of the fast memory. T sub s is the latency of the fast memory. T sub s is the latency of the slow memory. Alpha T sub s plus 1 minus alpha T sub s is the average latency, right? Let's just arbitrarily say that we want that to be K times the latency of the fast memory. And let's set K to 2, okay, and figure out what must alpha be. Well, that, of course, is going to depend on T sub f and T sub f. Plugging into T sub f and T sub s, 60 times 10 to the minus 9, which is the latency of DRAM, 60 billionths of a second, and 10 milliseconds for T sub s, which is the latency of a hard disk. And we want the system to perform with average half of the speed of the DRAM. So we're willing to give up half of it, and for the average latency to be 120 billionths of a second. What must alpha be? Guess what alpha has to be? 0.999995. That's how close to 1 alpha needs to be in order for the system to perform as if, as if it was running with all DRAM but twice as slow as the DRAM that we have. And that's still awful. Who wants a system that runs twice as slow as it would if you bought more memory? But notice how close this is to 1. So paging systems are exquisitely sensitive to misses, to hit rates being less than 1. Exquisitely sensitive. And the reason is that disks are so damn slow compared to DRAM. And the only way that this works is if you keep that hit rate very, very close to 1, much more so than in the cache. The difference in the cache was not quite as big. Okay, and that's why, you know, if you follow Gil Pratt's rule, you buy a processor that's half as fast as the fastest one you can get, and you buy as much DRAM as you can. Okay, spend your money on the DRAM, not on the processor, because that'll make more of a difference. Get it so that it never goes to disk. Okay. So paging's there just in case, but in general, it's a bad thing.
How much DRAM can you put in these modern computers?
It depends. Different ones take a different amount, but you can certainly put 128 in every system that's sold now. And in many, you can put up to a gigabyte. But you don't have to go that high. Just sort of, you know, go for the top of the line in terms of the amount of DRAM you're going to get, which these days is 128, perhaps even 256, okay? And go for a processor that's half as fast as the latest one, and you'll save a lot of bucks on that. Because people are dumb in general that are out there that are buying these things. It's not that they're uneducated, okay? And they don't know that the megahertz don't actually matter, okay? It's the performance that comes out that actually matters. Okay, if you look in the Hacker's Dictionary, you find this wonderful definition of the word thrash. To move wildly or violently without accomplishing anything useful. Paging or swapping systems that are overloaded waste most of their time moving data into and out of core. Core is the old little rings of magnetic stuff that used to store bits, as opposed to DRAM, rather than performing useful computation, and are therefore said to thrash. Someone who keeps changing his mind, especially about what to work on next, is said to be thrashing. A person frantically trying to execute too many tasks at once and not spending enough time on any single task may also be described as thrashing. Compare multitask. So that's a big joke, which is to say that an operating system which is trying to run too many programs at the same time often causes thrashing to happen. Okay, that's a whole nother topic to talk about how to build a paging system in an operating system that keeps changing what it's going to do. Okay, you guys all know that there is overhead to deciding I'm going to stop working on the bills and now I'm going to work on Ars Digita stuff, and I'm going to stop doing that and now I'm going to watch the news. And you know, and if you spend too much time flipping around from one to the other, the overhead will kill you. In the same way, this happens with paging systems. Okay, but let's assume that we don't thrash. How are we actually going to figure out which pages in the memory to replace? So it's time now to do that occasional thing and bring a page from the disk into the main memory of the system. This means that we have to decide which page in the main memory of the system to throw out. How are we going to do it? Well, we spoke last time in terms of cache replacement strategies about how great it would be to sort of throw out pages that were really old, because we believe that the locality principle says that pages that we access recently in the past are the most likely to be the ones that we will access recently in the future, or soon in the future, I should say. So one way of doing this, and a very easy way to do it, is first in, first out. We have this thing. I don't know how many of you know the story of Passover, but you know, this is sort of the angel of death here, going from house to house. This is the pointer of doom, so I put it in slightly less horrible terms. Okay. Actually, those of you who do know the story of Passover will absolutely love what's going to happen next, because it turns out that there's actually... So who would like to say what the story is of the final plague that happens in the story of Passover? Anybody here want to volunteer?
The killing of the firstborn son.
The killing of the firstborn son. It's actually, you know, the part of the Passover that I hate the most. And, you know, I'm like, boy, God is really tough, you know. He's an awful guy. But basically, because the Egyptians didn't let us go out into the wonderful desert where there wasn't any water. But anyway, out of bondage, the final plague was the killing of the firstborn son. And the implementation of the plague was that this angel of death went around from house to house, and wherever there was a firstborn son, he would be killed. But the difference was, at least the way that's written, and it's a very primitive story and kind of gross, is that we put a mark on our houses was to tell the angel of death to pass by and to go off to the other guys' houses and kill their firstborn sons. And we're going to see that, in fact, in paging systems, exactly the same thing happens. Okay? So, the pointer of doom goes around and around, and it says, guess what? You're the next one that gets thrown out of this nice, fast main memory, and we're going to page into your place right there. Okay? Boom, you're dead. Okay? And it writes it back out to the disk. And that's the next one that's used. This table is not the virtual to physical page table. This is, in fact, an inverse table, the physical to virtual page table. And so this is only keeping track. This has as many rows as there are physical pages in the system. And so the pointer of doom is just going around and around and around to each house, okay, getting rid of the entry that's here. And it has the virtual page number stored here so it knows where to write that page back into the disk before it comes back, okay? Where to look it up in the virtual to physical page table and set the valid bit to 0. Then it goes on to the next one. We should ask Shai. The Passover story, the final plague, Shai, what happens?
The final plague?
The final plague.
You mean where the kids get killed?
Yes, the worst one. The most shameful plague of all.
How do we get to this? The pointer of doom?
The pointer of doom. The angel of death goes around to every physical page and says, you're next. Okay, great.
The kids were just sent back to the main memory.
They were sent back to the disk, yes. The firstborn sons go, there we go.
Rugrats version.
Yeah, the Rugrats version. Okay, now, as there was in the cache, if you remember, there was a dirty bit in the cache. This is whether or not the kid has pooped in their diapers. If the page that you're about to write back into the disk has not been changed in the physical memory, do you need to write it back before you replace it? No. And so as a result, these physical to virtual page tables have a dirty bit to keep track of whether or not the page was written and whether or not you have to bother to write it back. And this is important because, remember, disk accesses take forever. 10 milliseconds is forever in the speed of a computer. So, is write-through practical? Remember, we talked about how caches could do write-through because writes are less frequent than reads. It's true for pages also, but remember, the whole trick is that if we write through a cache, every single time we write to the cache, we write to the main memory also, and we decide it's okay, we'll incur that 60 billionths of a second of latency on every write. What would happen in a paging system if every time the processor did a write, we had to wait 10 milliseconds? Even though writes happen 1/4 of the time, that would slow our system down much, much too much. And so you cannot do write through. So paging systems are always write back, and that's why they have this dirty bit over here. Okay, so Professor Corbido at MIT took the Passover story and decided to make it real and came up with this great idea for paging. And this was on a system called Multics at MIT, which was one of the first time-sharing systems with virtual memory in it. The pointer of doom would go around and around and around unless there was a mark on the house. And if there was a mark on the house, it would skip. Okay? And the way it worked is that it turns out first in, first out is not really what we want to do. If we want the hit ratio, the alpha, to be as high as possible, what we really want to do is something much closer to least recently used. What's the difference between first in, first out and least recently used? First in, first out says the next one to go is the last one that came in. Least recently used says the first one to go is the least recent one that was ever accessed. And that is constantly changing irrespective of when things were brought in. So we wanted some kind of mechanism that if a particular page was used frequently, the angel of death here would say, you know what, you've been used a lot. Even though you were brought in a long time ago, I'm going to skip you. And that's what the purpose of these touched bits are here, the T bits. So every time that a page is accessed in a system like this, whatever physical page is used, the touched bit is set to 1. Okay? And if the pointer of doom comes by a touched bit and it's set to 1, it skips over it.
Does it set it back, the touch bit back to 0?
That's an excellent question. What if it didn't do that? What if a program was particularly active and touched everything? The pointer of doom would go around and around and around and around and would say, uh-oh, you know, no Christmas lights in this town, so I have no pages to throw out. Well, I guess back then it wasn't Christmas lights, was it? No little idols of, you know, Egyptian gods. So what did it do? It sets the touch bit to 0. It skips over it, but it clears the touch bit. And what that means is that it is given a lease on life until the next time the pointer of doom comes around again. And it just keeps on going and going and going until it finds one that has the touch bit set to 0. And so it keeps going around, and when it does find one, which may be the very first one it did if they were all set, it then throws that one out. And go ahead.
So what causes the pointer of doom to move? Is it only when we need
When you
a new
need to
space?
replace a space. Yeah, there's actually
So
two
otherwise
ways
it
of
just
thinking
stays there
about
and
it.
sits around waiting?
Yeah, the technical term for this thing, it's actually called the clock pointer, but I don't use that term because it gives the idea that this thing is constantly moving, but it actually isn't. Okay, it stands still until we need to find a space in the physical memory of the machine in order to page a new page in, and then it starts to move. Okay? And it moves until it finds a touch bit set to 0. And if it sees one set to 1, it sets it to 0 and then moves on.
Once we know we need to throw something out, is the time to find an empty space inconsequential? Or
Yes, because keep in mind, again, it's going to be at least 20 milliseconds. Well, it's going to be at least 10. It's going to be 10 to page in a new page. It's going to be perhaps 20 if we need to write one out if it was dirty, and then page one back in. So that's a long time. So going around this thing with a little pointer is, in fact, very easy to do.
The first
Yeah.
thing we're checking for is when marking valid, so we don't have to worry about throwing.
Right. If it's not valid, we can go ahead and just use it. That's absolutely right. But if the system's been in operation for a while, all the physical pages are going to be used, assuming you didn't buy very much RAM. Now, if you bought plenty of RAM, you never have to do this, because you're never going to be looking for pages to throw out. Okay, which is, again, why you want to have lots of RAM in your system. Okay. Now, somebody asked a wonderful question, which was, doesn't all this looking in the virtual physical page table take time? And the answer is, of course it does. And so what we do is that we used an idea from caches called the translation look-aside buffer. And what this is a cache of this table. In the same way that the cache was a very fast RAM, but small, used to cache the main memory, we're going to cache the data that's in the table here with a small memory over here on the side. And this is the hardware that is part of the processor chip and has a few thousand rows in it. And as a cache, it's usually a fully associative cache, because it matters. You remember how much it mattered, because we're going through here all the time, that this cache have a hit. Okay, this is really a very, very high performance cache in most cases. And so it caches the entries inside of here. And only if we get a cache miss inside of here do we actually go into the table itself, which is stored in DRAM and may have multiple levels to it in order to look things up. In fact, usually the translation look-aside buffer and the cache exist sort of side by side, and it would be nice if the memory system were built in such a way that we could begin the lookup in the translation look-aside buffer cache at the same time that we begin the lookup here, even before we know the results of the TLB. How could we do that? We have a choice when we cache things. We can cache data items, and the tag inside the cache could have information corresponding to the virtual address, the red line here and the green line. I'm sorry, Sam, if you can't see it, but
on the top.
red is the middle one, and this is green here. Okay, I don't know if you can see this one at all, but this one down here is green, and this one over here is red. Okay, so if we take the black line and the red line and use those two as the tag in the cache, then the cache can get started on its work before this other stuff does its work, because it's doing the translation of V to M. But this is using V and the low order bits as the tag. Great. How about if this thing used the M bits, the green line, rather than the V bits for the tag? Could it also begin to do the work of trying to figure out if there's a cache hit or a cache miss? The naive answer is no. It has to wait until the virtual to physical translation is done, until it can compare the tag that comes in to the tag that's stored. That's the naive view. Now, why would you want the cache to be on this side of the virtual to physical page map instead of that side? Why would you want it closer to the memory bus? We actually said why in the last lecture.
Those tags are shorter?
That's one idea, yes, that's true, but that turns out to not be that big a deal. The number of bits here is a fairly small number. There's another reason the cache might want to be close to the memory bus, and that has to do with if there are multiple processors in the system. Remember the issue of keeping the caches coherent, keeping them synchronized with each other, so that if one processor did a write to its cache, and the data value was also had a copy stored in this cache here, that somehow this cache could be informed of that information over the memory bus. And the way that this cache would do it is by snooping, by listening to the memory bus. And when this other cache did a write through, this cache over here would observe the transaction on the memory bus and either invalidate its entry or actually write the new value in there. And that way the caches would all stay synced up with each other. Well, if the cache is using information from this side of the virtual to physical map, it's much easier for it to tell whether or not something that's going on the bus is meant for a copy that's in here. It can directly compare the bits in the address field on the memory bus to the tags that it has here. On the other hand, if it's way up here, it needs an inverse map in order to figure out if something that's going on down here on the bus corresponds to tag bits that are in here. So in fact, it is quite common in multiprocessor systems for the caches to logically be placed after the virtual to physical page map. And that sounds awful, because what it means is that we need to, on every access, every normal access inside of the processor, we need to do the translation first and then the lookup in the cache. And the cache is supposed to make things fast, but my God, this translation takes time. But that's only true until you look inside what's going on. So let's take a look inside the cache itself.
Are we talking specifically L2 caches?
Let's not worry for now. Let's assume that there's just one cache. And, but it's pretty much, yes, you are right, it's pretty much the L2 cache. Inside of this cache itself come in some bits. Okay, this is the offset page. Let me write this the right way. Offset in page. This is where within a page we are. And here's page number. Okay, these bits are combined and go into the cache unit. Here's the cache unit. Well, how do we actually treat these bits here? Whether we have a direct map cache or a set associative cache, we take these bits and we break them up again. And we break them up again into some low order bits. Remember, that's the hash function for the cache, which is then used as an index into the cache. And the cache may have, if it's a set associative cache, n different ways, but it's still going to take low order bits to figure out which row we want to use. And then it's going to compare one or more of the tags to see if they're equal to the high order bits over here to see whether or not we have a cache hit. Now, remember, the virtual to physical page map is operating on these top bits. And if we think about this clearly and look inside the box, as long as the number of bits in the offset in page is wider, is greater than the number of bits that we strip off here, we can think about this as actually consisting of bits that go down here and bits that go down here, and some of the extra bits, if this is wider than that is, come over to join us over here. Now, next question. Do we need to wait for this to finish before we can begin to do the read of this row? No. And that's fantastic, isn't it? So if we're clever about the design of the cache and the virtual memory system as a whole, then we can decide that the number of bits that we're going to use to index into the cache is less than the number of bits we use for the size of the page. And that way, this work, and remember this has the TLB going around it, right? The translation look-aside buffer, which is a cache itself. This can begin work at the same time that we do the read over here. They can both get started at the same time. And then when the answer percolates through both of them, we do the equal sign, which itself is a very fast thing. It's the read time that dominates how slow this thing is. And then we can see whether or not we have a cache hit. And so that's great because it means that the paging system does not add significantly to the time delay of the whole thing. Okay, and it's just because of this nice happenstance that it's the low order bits, the offset within the page, which are not translated, which are the very same bits that we can use to figure out which row in the cache to look at. Okay, so that's how we integrate the two with each other. Okay, this is what we learned today. Virtual memory has lots of uses. We can relocate a program. I didn't talk about that very much. It's sort of an operating system issue. But with that map, we can sort of reorder the order of the particular pages and make them appear anywhere we want in the virtual address space. We can have protection. We can stop programs from writing in the address space of each other. We can make the address space very sparse so we don't run out of room. And we can improve the performance versus a system that only used a disk. Back in the old days, programs used to run on magnetic drums, and there was actually an entire art to figuring out how to write a program so that the access time on the drum would be as fast as possible. Of course, if you use the DRAM as a cache for the disk, you're going to run much faster than you would just to the disk. In general, we need two tables in order to implement a virtual memory system. One is a virtual to physical page map, and the other one is a physical to virtual page map. Both of these, or at least this one here, may be a multi-level map. It's important to use pretty large block sizes compared to the block size that we had in the cache, because again, the latency of the disk is so incredibly slow. The replacement strategy must give us a hit rate, an alpha, that is very, very high. And the one that ends up being used in most cases is this mixture of LRU and FIFO. If you think about the touched bit, it's basically saying if the page is recently used, it will be skipped over by the pointer of doom, which is sort of a taste of least recently used. And we talked about how disks are so much slower. So that's the lecture for today.